So this is lecture 13, I believe, and so let's start. So maybe the key thing that we derived last time was an unambiguous ratio of the propagator with the same boundary conditions for two different problems. This was harmonic oscillator and this was free particle, and the ratio was e to the I by h bar S classical of harmonic oscillator upon same thing for the free particle times this simple quantity. And this was a good example to show that even though the normalization of the path integral measure d eta or dx is not very precisely defined, we can still get valuable information out of the path integral, because with this ratio, notice that this doesn't have any epsilons or undefined quantities or divergences or anything. It's completely finite quantity. With this result, which can be calculated purely from path integrals, and the denominator, which can be calculated from conventional quantum mechanics with operators, combining those two, we can get the numerator. So in that sense, the numerator can be thought of as a new result that we can get from path integral. Of course, we could have got it from the other way also, but it shows that the path integral can be self-contained if we are a little bit careful about what questions we want to ask. And now we'll pursue that theme. So what was the thing that made these two very easily solvable, both in path integral and in operator formalisms, is that both were Gaussian Hamiltonians. One was p squared by 2m, which is quadratic. Okay, let me actually, instead of saying Hamiltonian, let's say Lagrangian, because that's really what we want for this discussion. So L free particle is just half mx dot squared, and L harmonic oscillator is half mx dot squared minus half. So the Gaussian nature means that there's a square of x or x dot, and that this goes up in the exponent. And so we are basically evaluating something which you can schematically think of as dx e to the I integral x something x, and this is the Gaussian. Here there is some operator. That's what makes it Gaussian. So today we'll go beyond this, and what we'll consider is L. Now sometimes, okay, so there's a confusing language. We use the word Gaussian, but we also use the word linear approximation, because even though the Lagrangian is quadratic, the equations of motion are linear, because we lose 1 power of x when we take the equation of motion. So here it's x double dot equals 0, and here it's x double dot equals something times x. In both cases linear. So here we'll consider non-linear Lagrangians. So you have to understand that by non-linear, I don't mean that the Lagrangian is not quadratic or quadratic. I mean that whether Lagrangian is quadratic or higher order than quadratic. Higher order will be non-linear. So we'll break it in two parts. We'll just, for convenience, assume that the first part is what we already have been working with. And we'll add a new term. Okay, what we'll do maybe is just better is just we'll call this part v of x. Okay, and v of x, typically it may have a term like this, and then it can have higher order terms in x, like x cubed, x fourth, whatever. And these are the class of things for which now we want to understand how path integral works. So what are we going to do for this case? So of course, as you know, given any path integral, there's a very standard thing that you should start doing, which is to make the expansion that replaces the original action by classical action plus some fluctuations and expand in the fluctuations. And you can see that depending on how many powers this v of x has, you will get a number of terms in the fluctuation. While in these examples, which were Gaussian, we only got simple terms in the fluctuation. In fact, fluctuation looked exactly like the original Lagrangian, but that's a feature of quadratic Lagrangians. So let's start doing that. So of course the equation of motion of our, so let me write our Lagrangian here, half mx dot squared minus v of x. We are still working in one-dimensional non-relativistic physics, and we are just going on developing tools, and then we'll take it to more general situations. So the equation of motion, of course, is mx double dot is minus dv by dx. It's the easiest equation of motion possible. Okay, and now the first job is to find a classical solution. So solve with boundary conditions x at 0 equals xi and x at t equals xf. Now, once you have nonlinearity, there could be multiple classical solutions that do this. And even in systems where you don't have nonlinearity, there can be multiple classical solutions. Let me make a small digression just to show you when there can be multiple classical solutions. Okay. Supposing I consider the problem of a free particle. So it's in the free particle example that I discussed, but the particle is constrained to move on a circle. So this is x equals, let's say, 0. And let me choose xi equals 0 equals xf. You shouldn't think of this circle as, think of a bead on a wire. So it can only move in one direction, but that direction, though I'm calling it x, it's really theta. It's an angle. And don't think of gravity or anything acting on this. It's just a free particle with no forces. So we neglect all forces. But only thing is that its only possible motions are like this. Now I took very simple boundary conditions. So can you give me one classical solution right away? No motion at all. So x remains, starts here, ends here, and it's here for all the time from 0 to capital T. But now here's another one. X classical equals some constant times t. So let's call the constant k. So x starts here, and well, we have to decide which direction is increasing x. So let's say it increases in this direction. So after sorry, I meant t. Okay. Now to satisfy this boundary condition, after a time capital T, it must have come back here. So we will require that k times capital T is 2 pi n. Okay. In which case x satisfies these boundary conditions. So k is 2 pi n by t. And so this solution is 2 pi n by t, and the trivial solution is when n is 0. But n can be any integer, positive or negative. If it's positive, the particle can start here, go around and come back after one round, or in the time t it can go twice as fast and come after 2 rounds, or it can go the other way and come back after any number of rounds. And all of them are classical solutions, and none of them is really smoothly deformable to another because of the topology of the circle. You can't really continuously change a solution satisfying these boundary conditions with one n to any solution satisfying same boundary conditions with some other n. As soon as you try to vary this coefficient, n will stop being integer and it will not be a solution. We learn from this that classical solution doesn't only mean solving the equation of motion, which in this case is trivial, x double dot equals 0, but also solving the boundary conditions. And with these boundary conditions, there are infinitely many classical solutions. So in this situation, it's not even clear what is supposed to be the path integral prescription, but the correct answer is that u is equal to sum over classical solutions. Let's label them by I. Well, let's label them by n since we have an integer n here. E to the I s classical of n, and then path integral over fluctuations around that.
Sir,
yes?
What would be about the uniqueness for the
Uniqueness of?
The solution. There is more than one solution.
Infinitely many, I just wrote it.
So uniqueness?
Nothing uniqueness, there are infinitely many solutions. There's no unique solution. That's exactly the point I'm trying to make. Why should there be a unique solution?
For a given conditions?
No, that's the whole point. I gave you the initial conditions and you can see that what is a classical solution? It should solve the equation of motion, solve the boundary conditions. Does this do that job? It does, right? So it's a classical solution. You can see what's happening. Classical solution has to make the action stationary. Okay. Now, if I take some particle here and I imagine its path is swept out by a piece of string and I tie that string up like this, following the path, then that I can't shrink the string once it starts here and goes round and ends here. I can't shrink it further, so I can't get any other solution from this solution. So it is stationary. The point is that with any n, the action is stationary. That's why there are infinitely many solutions.
Can I say that classical solutions are locally stationary?
Yeah, but in this case, they're absolutely stationary because there's no stationary under continuous variations, because in the space of classical solutions, there's no solution I can find which will vary this given classical solution into another one as long as I retain the boundary conditions. So it's not just under local variations, it's absolutely a classical solution. And what I'm telling you here is a prescription what the path integral should be in that case. The idea is you pick one of those solutions, expand the action around it, perform this integral over that. This integral is unambiguous because eta is a fluctuation and it takes a value 0 at both ends. And it gives you the determinant as I've shown you before. But the answer here will depend on the classical solution, because if you remember, the operator O depends on the classical solution. So then I have to sum over whatever I get over all classical solutions. Now it may happen that one of them gives me the largest contribution to the answer. That's a next level question. But in principle, I have to sum over all classical solutions. Yes?
Since we have to make the first order variation of the action stationary,
yes.
Does that mean that there will always be a sum and it can never be like a continuous integral over different classical solutions?
Yeah, it's I don't know any obvious example where there's an integral over classical solutions. The sum can arise for two different reasons. One, that it can arise because of the topology, which is that of a circle, which has a very interesting topology, namely you can wind around it but only integral number of times. So then it's obviously a sum. But there could also be, in the space of classical solutions, there could be isolated minima. By minima I mean stationary points of the action, in which case I would again have a sum over those. But there could be very strange, well actually not so strange, now I realize that there are some problems where where there are a family of classical solutions labeled by a parameter, continuous parameter. Then I have to integrate over that, and actually that leads to something called collective coordinate method, which we are going to do in the second half of the course. So let's hold off on that. Okay? Any more questions? Okay, so that was a digression just to show you that there's no law about there being a single classical solution, and that the rule for evaluating path integral has to be generalized to a sum. Yes? No? Okay. Okay. Very good. Now let's get back to our problem of evaluating it for this potential. Okay. So now, suppose we have done that, then we are supposed to
So,
expand. Yes.
here you said boundary conditions, but you did not give us the x dot, right? And it's a second order differential equation. So that will uniquely determine.
No, I can give you x and x dot at the starting point, but I can also give you x at the starting and ending point. I have to give you two pieces of data. Yeah, many problems instead of this. So we are calculating the propagator, for which we are fixated on these boundary conditions. But we can calculate other things, in which case we may want the boundary conditions to be x and x dot at the initial point. And depending on the boundary conditions, we don't know a priori what classical solutions there will be. Okay, good. So now we write, next thing is to write S of x is S of x classical plus eta. Okay, so we assume x classical known, and yeah, this, and then this is equal to S classical, which my notation is S classical means S of x classical, which in turn is a function of t, by the way, that you should not forget, and then plus half m eta dot squared minus half v double prime of x eta squared plus order eta cubed. So let's proceed like this for some time. We'll neglect order eta cubed and higher. Let's try to understand how to do this problem. Now notice that in the approximation, is this clear, this expansion? I just have to expand that Lagrangian by inserting x equals x classical plus eta, and because it's a classical solution, there's no term linear in eta or eta dot, because the action is stationary. So the first fluctuation comes at squared power of eta and eta dot, and it's exactly that. Okay. So half comes because of second Taylor expansion of v of x around x classical. V of x classical, that is incorporated in here. Then the first fluctuation is 0 and the second one is here. Okay. So now notice that if we ignore this, in a few minutes we'll bring it back. First we ignore it. Then we have mapped the problem back to Gaussian. So in some sense, every non-Gaussian problem has an approximation which is Gaussian, and in that approximation, u is equal to e to the I s classical integral d eta e to the I by h bar integral 0 to t dt, and then eta of t, then some differential operator minus m by 2 del t squared minus half v double prime of x classical. So this was x classical eta. Okay, you see how this compares with what we already did. We've done this when v was not there, so we just got this. This was our operator which we had called O. And we've done it when v was quadratic. In that case, we just got its second derivative, which was just the term m omega squared, which was a constant. So then we got this plus a constant. Okay?
There should be a plus sign.
Plus sign. Where? Here? No.
The second
Because
one.
this? No, this is the...
There is an overall negative sign.
Where's the overall negative sign?
There will be a minus of all of this, and
Yeah, I could take these two negative signs and put them out, but I think this is correct. I start with e to the is, right?
yeah.
This comes minus because of one partial integration of d by dt,
Oh right.
and this is already minus. So I think this is okay. And this motivates us to define an operator O of t and t prime which is Im by h bar del t squared plus 1 by m v double prime on delta of t minus t prime. And with this definition, this thing is equal to, I'm going to drop this factor e to the is classical. It's not part of my calculation from now on. It'll always be there. I'll put it back at the end. Okay. So the rest of it is the integral d eta e to the I. So now this thing I've defined this to be my operator. So then it's e to the minus half integral dt prime eta of t o of t prime eta of t prime, just like we always had. Okay, just that o has changed by this term. All clear? Good. Okay, and so of course this we already know. The answer to this is det to the minus half of O upon 2 pi, just as it always was. But now the det is going to be a bit more fun, because the dets that we dealt with had either only del t squared or del t squared plus a constant. In both cases, we had to solve analog of a Schrodinger equation, but with no potential or a constant potential. Now we have a potential where this is a function of x classical, which is a function of t. So therefore there's a t dependent term here, which makes it the analog of a Schrodinger equation for a t dependent, for a x dependent potential. In the Schrodinger equation language, the potential is non-trivial. Remember, now there are two potentials in this problem. This v is the actual potential of our physical problem, but this is going to lead to a Schrodinger equation with a potential which is this function of t. So we have to work that out. And so to find the eigenfunctions and eigenvalues, in particular we want the eigenvalues because that is how we find this determinant. So the eigenvalue equation is now Im by h bar del t squared plus 1 by m v double prime x classical of t. And this is the analog of, so this on, if you like, on psi n of t will be equal to lambda n psi n of t. And once we solve this eigenvalue equation, we'll find the lambdas, then we'll put them here, then we'll take the product over all of them, and then we'll take the minus half power, and that's the answer to this integral. And then we'll put back e to the is, and we've got our answer to lowest order of our non-Gaussian problem. So it was pretty easy, I think. Everything lies in the details. X classical may or may not be easy to find. The classical solution for this Lagrangian may or may not be easy to find. For example, if it is a quartic potential, V of x has x squared and x fourth in it, then the solution, classical solution with such boundary conditions, is an Jacobi elliptic function. But this doesn't necessarily mean we have to be experts in maths. We can just go somewhere and look up such equations and find out from somebody else that it's a certain function. And all we care really is we don't even care much about the function. We want to put that function back in the Lagrangian and integrate it to find S classical. And how well we can do that, well, it's up to us. We could do it analytically if we have enough mathematical power. We could try to do it numerically. There are all kinds of ways to do it. I want to emphasize, though, that this is not the difficult part conceptually, because given an action, finding a classical solution and putting it back in the action, well, there's nothing very subtle about that. It's just a matter of solving some equations. The fun is really in this integral, which is embodying the quantum aspect of the problem. So this expansion that we've been discussing, in specifically x is to replaced by x classical plus eta, is called the semi-classical expansion. And the conceptual idea is that here's the classical part and everything in here is the quantum part. Okay, we don't use any kind of quantum mechanics or even path integral to get this. It's just a classical number. Here we have to actually evaluate a path integral. And that's where all the quantum features of physics come in. Now you can already guess that this determinant is going to be badly divergent because its eigenvalues of this equation will probably grow. Although you could also be creative and try to find some equations which have very good eigenvalues, but typically they would grow. But then again, what would we do? We would like to take the ratio of this determinant to that of the free particle, and maybe we can make that ratio well defined. And if we can do that, then we have solved this problem, non-Gaussian problem, for quite generic V, subject to knowing X classical well enough to find this, as well as, more important, well enough to solve this eigenvalue problem. Here you need to know X classical really well, because the eigenvalue problem depends entirely on what is X classical. Okay, but all this was done in an approximation where we neglected the cubic terms. And so you could ask that, how have we really done anything really non-Gaussian? And the answer is yes, the non-Gaussian nature of the Hamiltonian, which is like all the terms beyond, or the Lagrangian, which is like all the terms beyond quadratic inside V of X, is used in this function. So this depends on everything in V, not just the leading terms, but also this depends because the classical solution also depends on that. So in two ways, the answer depends on the non-Gaussian features of the Hamiltonian, but in a third way it doesn't. And that third way was the fact that we dropped, when we made this expansion, we dropped these terms. So now we should come back and ask what to do if we want to keep those terms. Okay? Any questions? Okay. If you remind me sometime in the future, because I didn't, maybe in field theory I'll be doing this, we'll also like to understand what is the dependence of the theory on the coefficient of such terms. So what we are going to do now is to just put in a number lambda, which will treat as small, because right, when we neglected this, we should have some justification. So if there's a number lambda, we can say in the limit lambda goes to 0, this is not there, and all that I've done is okay. And now we want to work order by order in lambda. So we are going to develop what is called perturbation theory. And this perturbation theory, since it's for an elementary quantum mechanics problem of such an elementary Lagrangian, it will be much easier than the perturbation theory of QFT that you've already learnt, which is Feynman diagrams. Even this problem has Feynman diagrams, and we'll see those in a little while.
Sir,
Yes.
when we put explicitly X classical as a function of t,
Yes.
for if there exist many such solutions,
Yes.
then we put the summation.
No. We put X classical as a function. So I told you, we evaluate everything on one classical solution, and the whole answer is summed up.
Okay.
So right now I have one S classical sitting here. Everything here depends on the unique X classical corresponding to this S classical. And then I'll get an answer, I'll get a determinant. And then if there's another solution, this will be another S classical with another determinant. And I'll take all of those and add the whole lot. And basically what is it saying if you think physically? It's saying that the particle, to get from here to here, our first statement was, in the path integral language, that the particle gets from here to here by picking any path it feels like. Fine. Those are nice words, but there are not a lot of calculation we can put behind those words. Then we say something more sophisticated. We say, no, the particle really wants to get from here to there by extremizing its path. And that's what it would do if the world was classical. But our world is semi-classical, which means the quantum effects are there, but not too big. So the particle really does that. And then we take account of the possible fluctuations around that classical trajectory which the particle wants to take. But now when we have multiple classical solutions, then we say, well, the particle even in classical physics is not sure what it wants to do. It might want to go like that, or it might want to go around the universe and come there, or it might want to, and all of those are classical solutions. And now I'll have to separately study the fluctuation around each of those classical paths. Every time I integrate over eta, I'm integrating over some fluctuation around the classical path. So that's sort of the basic idea. And just to give you a little preview, it does become clear in physics problems that out of all classical paths, the one that gives the largest contribution is the sort of simplest path. So this particle going around a circle, you can get lots of contributions because there are infinitely many classical paths, but you see that the action will be larger and larger for those paths. Okay. So at least in, we'll have to do this later, but in some stationary phase approximation, which is similar to saying that instead of I, we imagine a minus sign, then you see this factor e to the minus s classical. If one s classical is large and the other is small, we have to keep the smallest one, because then the larger one is heavily damped exponentially compared to the smallest one. So in practice, we often work with what we call as one saddle point or one or two saddle points. But it can also happen in field theory that there are a few different saddle points, and as we vary the parameters, which one is dominant may change. So this is why the whole business of doing field theory involves a lot of thinking at all times. So there are problems in physical problems involving black hole physics and so on, where you think you have got an answer, then you realize the answer looks very contradictory. Then you realize that no, you were extrapolating the parameter to a region where the dominant saddle point was a different one from the one you took. So which classical solution you take is a matter of judgment about which is smaller. So we'll see that in explicit examples. At some point you'll be asked to evaluate, for example, that particle on a circle, all its classical actions, and you can see which one is the smallest of all of them. Yeah.
So you said that there are examples of continuous classical action variation, right?
Yeah.
That depends on them.
Yeah.
So in that case, how will you take the variations, because they are?
Yeah, it's a base. So that's what is called a flat direction. In that case, we have to actually do something else. So it's a bit complicated for just now, but we'll come to it. We'll come to it pretty soon. So let's assume those are not the case right now. Okay, now we can easily move on. So now the question arises how to incorporate this term. So let's start with that. So let's now assume same Lagrangian. We've done everything, but we didn't do the eta integral yet. So we got the answer u is equal to e to the I s classical by h bar, and we have an eta integral, and it contains e to the minus half integral eta o eta, but it also has another term which we could call, so this is all like this, which could be minus I over h bar integral dt v triple prime. Now this Taylor expansion comes with a factor 3 factorial, I guess, of x classical eta cubed. Does this look right? Just a higher order. This contained v double prime, but I had stopped there. So now I'll go to v triple prime. So now I don't know how to do the integral anymore. Up to here, if I did the integral, there were two etas and an o, so it was dead to the minus half of o. That's a simple rule. But now what do I do? Well, the answer is very easy. The answer is, let's generalize L to or generalize the integral to a slightly more complicated one. Okay, first of all, I think better, simpler answer. Yes.
That's probably because we took the Lagrangian, so
No, this is e to the minus this term. Huh? That is its own, doing its own. This is the bracket e to the all this. So this is I by h bar in the action, and then minus because v came with a minus, and then it's v triple prime. So there's no this doesn't know anything about the other terms.
but the Lagrangian minus v.
At minus v, yes.
So minus and minus.
Why two minuses? One minus. This is the minus of minus v.
Okay, yeah.
There's no other minus. Okay. So now what I do is, I say, okay, this is exponential of that and this. Remember one beautiful thing in path integrals, there are no operators anywhere in sight. All these are functions. Everything commutes. Anything which you can do with functions, you can do with this. So you can separate the exponentials into e to that and e to this. And this exponential you can write as summation minus IH bar upon 3 factorial to the n equals 0 to infinity, integral v triple prime x classical over dt, sorry, eta cubed. So v depends on t, remember, everything depends on t, then we integrate dt and we take this to the nth power. Simply the power series expansion of the exponential. Okay? And from this point of view,
There will be an extra n factorial.
there will be an extra n factorial here. Thank you. That's the exponential n factorial. And then everything is just to the power n. I took the constants here and the t dependent stuff there. And now when n is 0, then this is all 1, and that's what we have calculated. So now we should let n be 1, 2, 3 and ask how to calculate these things.
It should be minus I by h.
Minus I by h. Thank you, thank you. Yes. Very good. Yes. So this is what we want to calculate. But now if you look at this, for any n, what I can do is I need to calculate that integral d eta e to the minus half. Now I'm going to write it as eta o eta. You're supposed to understand by this double integral with eta and eta prime. Okay, and now here I will have eta t1 cubed to the eta tn cubed, and then outside I will integrate all these t1 to tn, and here I'll put all the factors including and v's will come here in this integral. So v classical depends on x classical, which depends on t, so I'm going to write it directly as a function of t. So they'll all come here. Is it clear what I have done? I have the nth power of this object, but the only thing which cares about the path integral is eta cubed. Everything else doesn't see this path integration, d eta. So I'll keep the path integral, it's over this, and then lots of eta cubes. And then everything else I just put outside, and there's a lot of work to evaluate all these things. But the job right now is how do we evaluate this path integral. So it's a new path integral, just like the old one which was det, but it has lots of etas downstairs. Okay? And this is only from the cubic term, but of course there are still more terms. There could be v to the 4th derivative and eta to the 4th. And in fact, often that will come because this might even be 0 for some reason, like if the potential doesn't have a cubic term. So it could be anything, but this term alone, let's just take as a test case. So this is the integral we need to do. Yeah. So now let's try to understand how to do it. For that, yes, please.
Could you explain how you expanded that out once more?
Yeah, it's just e to the x is summation x to the n over n factorial. That's all I did.
So there will be an extra summation of all the n outside all the integrals. Right?
All the n. This whole thing is x.
Yes.
So I'm writing this as summation x to the n upon n factorial.
Right.
So x is all the stuff here which is raised to the nth power, and that's the n factorial.
So when you bring it here in the
This one.
Yeah.
In this one, what I have done is, when I have a nth power of an integral, then I have to multiply n of these integrals.
Right.
But now it's very confusing if I keep the same name t for the integration variable. So in each of them, I change the name of t to t1, t2, t3. And so I get n integrals. And here I put n different things at different times because I'm taking n.
There is a summation and 1 by n factorial.
Of course. No. So actually, I think I said that. So only summation and 1 by n factorial. Yeah, absolutely, it's there. It's there. So yes. So I think I was saying that the nth term for a fixed n is this.
Okay.
Yeah, and then I'll sum. So yeah, I can make you happy by just writing this and this. Right? Okay. Good. So how do we want to do it? So it helps to have an analogy. So for this, we think of multivariable Gaussian integral. And in fact, you should always keep that analogy in your mind. And by the way, I remembered what is the second thing I want to discuss tomorrow in the tutorial, which is the relation between ordinary integrals and derivatives and path integrals and functional derivatives, so that you fix it in your mind. I mean, I've been using it all this time, but I feel that people have not completely got it. So multivariable Gaussian, we'll do more tomorrow. So the Gaussian itself is, I have, let's say, n completely independent variables, and all are integrated from minus to plus infinity. And the first step, I can have minus half xi aij xj, where I and j are summed over. I don't write the sum, and there are n of them. And you see that actually that's exactly the discrete version of this. O is the analog of A, and it has two arguments instead of indices, and then these have the argument t and t prime, and then instead of summing, I'm integrating. Everything else is the same. And this, of course, is very trivial. This, by going to eigenvalues, is det to the minus half of A, the matrix, upon 2 pi. That's the whole reason why we, in the first place, started talking of det O. Now the question arises, what if I want, so this is okay, this is easy, but suppose I want integral dx1 to dxn, then times xi1 to xik, then times this exponential. Okay, I is not a good name for here. P1 to pk. And then e to the minus half xi aij xj. Suppose you want to calculate this, where this could be anything. It could be a single, any one of the x's, or any product of any two, or one of them to some power, another to some power, just any polynomial in all these x's. Supposing I want to calculate it, what's a smart way to do that? Are you familiar with the smart way to do that? Then I could skip quite a lot, no? Okay. So then we'll do it.
By the parameter A.
Say again?
Differentiate by parameter A and find out the...
Yeah, not by parameter A though. A is a matrix.
So the single variable version of that would be...
Exactly. So I generalize my original integral to integral dx1 dxn e to the minus half, this is what it was, and then I add plus ji xi. where j are some constants. Okay, they will be called source terms later, but right now they are just some constants. And now I note that if I want to calculate this thing, let's write it here. So this I'm going to write as product dxi. It's not a path integral, it's just an ordinary integral. And now I have here xp1 up to xpk e to the minus half xi aij xj. This is just the same as evaluating this integral without these insertions, but with this extra j term, and I differentiate in j p1 up to j pk, and then I set j I all equals 0. So why is this equality true? Well, in this one, whenever I differentiate by some j, the corresponding x comes down. And so the jp1 will bring me xp1, jp2 will bring me xp2. I keep doing that till I have got xpk. And then once I have got everything down, then I set j equals 0. So this term goes away. And then I'm back to what I wanted. So in that way, this is the object that I want to solve for. Because once I solve for this, then differentiating in it is easy. Differentiating is always easy. It's integration which is hard. Okay, so let's do it and write the answer. Now the beautiful part is that the integral is no more difficult after I added this than it was before. Before it was a det. Now what I have to do is to complete the square, because it's quadratic in x and linear in x. And when I complete the square, I always get an extra term to compensate, and then it will be back to this integral which I already know. So completing the square, very easy exercise. We actually get, so we have to do that, we define x tilde of I is xi plus, okay, I'm never going to be able to do this. Yeah, A inverse J. I better not try to do it live, but the answer for this box bracket is equal to e to the plus half ji A inverse ij jj, and then the old integral. Actually, this x is not the same as this x. It's the one after I completed the square, but then I renamed it back to x. Okay, and this is the extra term. It's very easy. It's just a bit of mess of indices, and I don't trust myself right now to get that mess right. But this is a result in ordinary Gaussian integration, and you're in your 4th year at least, so you certainly know ordinary Gaussian integration backwards, and this is the result.
So
yes.
So here you have diagonalized it, and in the new coordinates you have completed this.
Was not necessary to diagonalize it even. All I needed to know was that A can be inverted. I'll come to that in a minute. So this is if A is invertible. Basically, I shift x to x, xi. So as a vector, x shifts to j A inverse x or A inverse jx. This is what I was worried about. Yeah, x. So if I do that, then this term picks up an, this gets an A inverse j, this gets an A inverse j. Sorry, that's not what I wanted to write. X minus A inverse j. Sorry, yes. Or plus in this case. So if I replace x by x goes to x prime equals x minus A inverse J, or plus, maybe plus. Then if I put that here, then A times A inverse is 1 and I get xjx. But when I shift this one, I get the same thing. So I get twice of it. That cancels this and that's completing the square. But then there's the term A inverse J times A inverse J. And one of the A inverses cancels and I get J A inverse J. That's the schematic idea. But I really think this is a very important thing for you to do yourselves. I really cannot do that here. Okay. But this is nice because this answer, and remember everything's integrated from minus to plus infinity. So after shifting it, this x prime I just put back, I rename it back as x. And this is my old friend det of minus half of A upon 2 pi. So this is the extra. And this doesn't care about the differentiation business. So this is the only thing I need to differentiate. And when I differentiate this in J, the first time I get A inverse J down and then the exponential back. Exponentials always stay when I differentiate them. Next time I differentiate in J, I'll either differentiate a J from upstairs or a J which came down. So there'll be few terms and so I have to just do it. Specific example is that if I want just 2 points, so x p1 x p2 integral. This is easy to carry out explicitly. So this, for this, I have to take e to the half. So I remove these as per this formula and I put these del by del j's outside the path integral. And so this is, then I do the path integral and I get J A inverse J. I've written the indices here, times det. And now det isn't going to do anything. That is just going to sit there while we differentiate. And we are going to differentiate J P1, J P2. And this is Ji, Aij, J. Okay. And then we are also going to set J equals 0 when we finish. So J equals 0. I shouldn't put this bar here. I should put it at the end of everything. So now what happens? The first one will pull out Aij inverse Jj with a factor of 2 because this could have hit this one or that one. And so I'll get A P1 J J J and e to the same thing. So det to the minus half. Sorry? It's A inverse, correct. And this is after doing one after del by del J P1 only. I get this answer. I still don't set J equals 0. I have to finish all my differentiations and only then. So now I have to differentiate in JP2. Now if I differentiated any of this with respect to JP2, I'd be in trouble because when I set J equals 0, this is going to vanish. So there's no contribution. So I must differentiate this one and only this one. And so I get A inverse P1 P2 times e to the half J A J times det to the minus half A upon 2 pi. And now I can set J equals 0 and this term is gone. And so that's my answer. So we've already learnt that integral d eta, eta at t1, eta at t2 is, so now of course I have to just transport this to the infinite dimensional or path integral case. This was the finite integral case. And so it's just O inverse, so this is times e to the minus half eta O eta. And the answer is O inverse of t1, t2, z to the minus half of O by 2 pi. So we just found how to insert 2 etas. We could have done 1 eta for simplicity, but as I said, that one will give you 0 because the result of one differentiation is this. And when I set J equals 0, it just goes away. So 1 eta inserted here is 0 and 2 etas inserted here is non-zero, and that's the answer. This is the answer. Now remember, the integral without any etas inserted, something we've done for the last couple of lectures, this was just z to the minus half of O by 2 pi. So if we take the ratio of these two integrals, path integral with two etas inserted, path integral without any etas inserted, then that ratio, which is d eta t1, eta t2, e to the divided by same thing without the etas, then these det factors cancel and the answer is simply O inverse of T1, T2. As simple as that. And that's beautiful because the quantity on the left is defined to be, is denoted as the 2-point function or correlation function of etas. 2-point function. And I should stop here. We just found an explicit formula for the 2-point correlation function of etas in the path integral. But what should you all be excited about? What is it that you should now go out from the classroom and dance on the lawns of ISER? Why? Because the det has cancelled out. So the problem of calculating and multiplying infinitely many eigenvalues is gone. With it, any infinite things are gone, as long as O is invertible. Okay, if O is invertible, you got your answer. And here's one more example of something the path integral can calculate for you without knowing too much about the measure integral d eta, because we normalized this by this. By normalizing it by what we call the vacuum or empty path integral, we got some kind of statistical average, and that's the answer. Now, what good is it in physics? That we'll still have to see, but we got an answer. Okay, and there's a very easy one more step, but there's no time today to do it, where I can tell you how to get higher point functions by the same method. So we'll just complete that on Thursday. So this is how the non-Gaussian path integral is done. I'm just trying to remember some comment. What if O is non-invertible? That's the only thing to worry. So for that, we go back to the original Gaussian integral. What if this A has determinant 0? Then of course I can't take out this A inverse. This whole thing falls apart. But if A has determinant 0, it means it has at least one 0 eigenvalue. So if I go to the eigenvalue basis, there'll be one integral from minus to plus infinity where there's nothing up here. So that integral diverges. So it's a real problem in the sense, if O had a 0 eigenvalue, the path integral diverges in a hopeless way. Hopeless in the sense, it's supposed to diverge and it diverges. So obviously you can't find A inverse, obviously you can't find O inverse. But then we have to look at the physics of the situation and decide what to do, and we'll be looking at such situations many times in the next few lectures. Questions? Yeah. It's already symmetric because it's multiplying xi xj. So if there was any anti-symmetric part, that wouldn't even appear. Same is true for O. You can as well say that if you choose it symmetric, or you can choose it how you like, but only the symmetric part of it enters this in this thing. If I multiply by xi and xj, it's symmetrized, gets symmetrized automatically. So there's no problem then if it's symmetric, real symmetric, then of course it's Hermitian, then it has eigenvalues, so, and it's diagonalizable, and all those things follow.
So what would a what would a 0 eigenvalue operator physically correspond to?
Yeah, so that, as I said, it's a long story and we'll have to come to it. It has something, okay, so I can just give you the short answer. It has to do with the existence of a continuous family of classical solutions. So supposing the classical solution has a parameter in it which is arbitrary, then by varying that parameter I have a continuous family of classical solutions. But remember, these are fluctuations around a classical solution. Now if fluctuation in the path, Now, if I vary a path in a direction which takes me to a new classical solution, then obviously I'm not getting, it's not a fluctuation, it's still on a classical solution. That's the root cause of zero eigenvalues. So families of classical solutions lead to zero eigenvalues.
So like the variation of the action on the path is still zero.
Yeah.
But the parameter is taking it to a new.
The parameter takes it to a new path where still the variation of the action is zero.
Right.
So that's the new parameter. So it's orthogonal to the path in a sense. I mean, the path is like this, then you vary it to a neighboring path, but that neighboring path remains a classical solution. That's not normal, but it can happen in many problems. It's not normal in the sense if you just think of a free particle is going to go in a straight line. Why would another path be a classical solution? It's also not like the particle on a circle, because that no small variation of the path can give you a new classical path. In that case, those paths labeled by n are all disconnected in disconnected sectors. But there could be physics problems where the actual path you can vary a little bit and get again in some direction and get another classical solution. And that's when the determinant of fluctuations develops a zero eigenvalue, saying exactly that the direction you are fluctuating in is actually a classical solution. So it's saying, silly fool, why do you have a fluctuation for that direction? And this is one of the beautiful things about path integrals, that everything which goes wrong from now on usually has a physics explanation and a physics solution. Yeah.